Hey, welcome back to Fat Mama Physics. Here we have another video on work and energy. So in this video, I will be doing going over these examples. There won't be anyone for you to try, but you are welcome to pause the video anytime to try the rest of the problem. It's just I won't be prompting you on that. So, example 3 and 4, let's go. Example 3, a 2012 Paralympic champion lifted a 285.5 kilogram mass 55 centimeters upwards. What is the minimum work done against gravity in the lifting process? So we need to draw a free body diagram. So let's do that. Here we have some dumbbells here. I'm just going to draw the dumbbells and not the person just to make it look simpler. And this person is lifting it up to here. In the process, so let's draw the free body diagram. We have the force due to gravity as well as the lifting force. This part of the question might be confusing. What is the minimum work done against gravity in the lifting process? Since we are talking about the lifting, we can say what is the minimum lifting force that we need to get this mass to move up, or at least to go up 55 centimeters. So that is to lift this dumbbell up. You can accelerate it upwards, or you can lift it up at constant speed, assuming it is already moving. That you might have to assume. Which one is easier? Probably lifting at constant speed, which means the acceleration is 0. And if that's the case, the lifting force is going to be exactly equal to the force due to gravity. So in terms of the work done, this will probably be the lifting force times the displacement, which is directly upwards, which means we don't need to use a cosine theta. Cosine theta the theta will be 0, and cosine of 0 is just equal to 1. So 1 times anything is just that thing itself. We don't even need the cosine value in here. It's redundant. So then the lifting force, since it's equal to Fg, we can use Fg instead. Fg, we know, is equal to mass times gravity, in which gravity is 9.81 meters per second squared. So then this becomes mass mgs. So close, MSG. Why not? Because if you multiply, order doesn't matter, right? So the mass we have 285.5, gravity is 9.81, and displacement is 55 centimeters, which we need to convert to meters by dividing by 100, giving us 0.55 meters. And putting in the calculator gives us 1540, which rounds up to 1500 joules. 2 reasons why I wanted to do this problem. Number 1, the direction of the force is not sideways, it's now up and down, which then allows us to see how the force of gravity plays into this. In fact, you're going to see something very similar to MGS later in another lesson when we talk about potential energy. More on that later, so keep this one in mind. Next up, we have example 4. It's a conceptual problem. A man carries a 95 kilogram refrigerator at a constant height of 1.5 meters above the horizontal ground. Assume he carries it at a constant speed of 0.25 meters per second. How much work does he do on the refrigerator carrying it a distance of 120 meters? Assume the refrigerator experiences no resistive forces such as air resistance. Interesting. Why don't we draw a free body diagram first? So on the refrigerator, there is a force due to gravity acting on it. This man is lifting it up. We know there is no resistive forces playing against the refrigerator, and since the refrigerator moving with a man is at constant speed, there is no net force in the forward direction, meaning that if there's no resistive forces, there is no forward force acting on this refrigerator at all. So these 2 forces are the only ones acting on the refrigerator. So going back to the question, we want to find the work that the man does lifting the refrigerator 120 meters. So the FL, the lifting force, is what we need. And since the refrigerator is not accelerating up and down, it looks like the lifting force is equal to the force due to gravity, which is just mass times gravity here. The displacement we have is 120 meters. But here's the interesting part. the lifting force is directly upwards. The refrigerator is being displaced horizontally, which means the angle between the two, the force, lifting force, and the displacement is 90 degrees. Oh. Well, let's try this out. Since the lifting force is mg, let's just put it in. The mass is 95 kilograms. Gravity is 9.81. Displacement 120 meters. And cosine 90. Well, let's just, before we calculate all this, let's take a look at what cosine 90 is. Putting in the calculator, we get cosine 90 equals to... it's 0. Cosine 90 is equal to 0. What is anything multiplied by 0? You're right, it is 0, which means this whole thing is 0. What? Are you telling me that this man here is doing no work in moving this refrigerator to the side 120 meters? That's just really weird. It must be really hard for him to do all that work. But wait, what does work really mean? Work is the ability to change the energy in a system. So if work is done on the system's energy level will go up. Well, let's think about it. Is the energy in this refrigerator increasing or decreasing? It's going at constant speed, so it's not really gaining any motion energy, which we'll talk about later. That's called kinetic energy. So it's not gaining any kinetic energy. The man is not really pushing the elevator up or down. So it's not gaining anything we call gravitational potential energy, which is something we will talk about later as well. Is the refrigerator heating up? No, the man can't heat up the refrigerator. The refrigerator is not gaining any chemical energy, any other sort of energy. It's not gaining energy due to the man moving it. So that means this refrigerator is not gaining energy at all. It's not gaining energy, which means by definition, no work is being done. But you might be thinking, oh, but the man's working really hard there. Well, guess what? We only care about the refrigerator right now. The refrigerator doesn't care how much the man is doing. The fact that we are just humans that uses muscle to do all our work and our muscles feel the pain and burn just makes us biological. If I had substituted this man with a robot, the robot wouldn't be feeling anything. Well, it's inanimate. But the key thing is we have to think about work differently than how we think about work in relation to us as humans. And that's a perspective change. And the other thing to look out for is the fact that the lifting force has no component of it in the direction of displacement. So by definition, this force does nothing in terms of doing work on this refrigerator or doing useful work on the refrigerator going in that direction. Hence, cosine 90 being 0. So the two key ideas in this question is the fact that the refrigerator is not gaining energy, therefore the work done on it equals to 0. Mathematically, what that means is the fact that the lifting force was perpendicular to the direction of displacement, meaning that this lifting force did no useful work in moving the object forward. Cosine 90 equals 0. And if you're thinking, well, what if the refrigerator was accelerating? Yes, if the refrigerator was accelerating, then the man would have had to exert a lifting force in a diagonal direction in order to do that, which then a component of that force would be in the direction of displacement, meaning that there would be work done, but not in this case. The refrigerator is not accelerating. So hopefully these two questions gives you some insight into what work and energy does and how they relate to one another. Thank you for watching this video, and I will see you back for another work and energy problem. Fan Mama Physics signing out.